Okay, hello everyone and welcome to Handmade Hero, the code, that's good. The show where we code a complete game live on stream, except for when we're on RSI break, which we are right now. And so what I've been doing, rather than just being off the air completely, is taking questions from people like we do on the normal show, but instead of having the programming, we just have the questions. Since I can write just fine with my right hand, not a problem. It's really only the left hand that's busted. So, without further ado, I will talk about something that I got a question on in email, which is pretty straightforward to explain, but is somewhat complicated to implement due to really the ambiguity of it. And I'll try to explain why that's the case, although certainly it's a lot better understood now than it used to be. Anyway, Elvin was asking about inverse kinematics. And essentially his question was very broad. It was like, I don't know what this is. Like, what does that mean? What's, like, explain. Tell me about this. What is it? How does it work? Why do we care about it, right? And I think that's a pretty reasonable question. If you've never worked on character animation before or robotics, you probably don't really know what this is, and you have some vague notion of what it is, perhaps because you use it in some kind of a tool, like an art tool or something, but it's not really clear what that means in code or where the term comes from or any of that stuff. All right. So inverse kinematics is actually exactly what its name implies. It's just if you don't know what this term means, then you wouldn't know why inverting that makes any sense. So let's start by talking about the term kinematics and what it means in this case. So the term kinematics in this context is talking about the concept that for many of the things that we care about in computer graphics or robotics, where you have what would be called a multi-link assembly, which you might colloquially refer to on your own body as an arm, let's say, or a leg, right? Something that's sort of got multiple pieces to it which can move independent of each other in some ways, but dependent on each other in other ways. This is what we are talking about when we talk about kinematics. We're talking about taking one of these things and figuring out where it is when we know its joint angles, or rather the parameters that describe its state. So for example, if I was to imagine sort of my arm, right? Here's Casey, and here's my shoulder, and I was to imagine my arm coming down here to my elbow, coming up here to my hand, yeah? If I was to talk about that, we could say that this was a two-link assembly, right? Here is link 1, and here is link 2, right? Link 1 is, for the purposes of this discussion, if we're just talking about just the arm, it's rigidly attached right here, right? Meaning it can't, there's nothing I can do to move my shoulder out of its socket that's not going to be incredibly painful and very dangerous to me. So for all intents and purposes, my shoulder socket is like a fixed location, and the arm comes out of that, right? And it's a rigid bone. But it comes down to an elbow, and the elbow can bend, right? So there's another degree of movement that can happen here. So this, as we all know, my shoulder is kind of like a ball and socket joint, so it's locked in position, but it can rotate around. And then the same thing is true here. This is connected fairly rigidly. It can't be separated, but it can be rotated in at least one way, and sort of to a limited extent in another way, right? So this has got some degrees of freedom on it as well. And by the way, I should define that term. We talk about that a bunch in this context, so I'm going to talk about what that means in a second here. So let's put that on the board. So if we're to talk about this in isolation, here is the hand, here is the shoulder, here is the elbow. Then what do we need to know to figure out where the hand is? Well, if we simplify this for the sake of the diagram, although this does not simplify, or sorry, it doesn't change the nomenclature or anything else, but if we just simplify it for sake of diagram and say this is 2D, we might say that, well, we need to know the angle that the shoulder is coming out of the arm socket, right? Like maybe we need to know how much I've lifted my arm, right? So as I come this direction. And similarly, I would need to know how wide my elbow is opened. So I've got a certain angle here that I need to know and a certain angle here that I need to know. But at that point, for this very simplified model of an arm we've constructed, if I know these two things, then I know for any position of the shoulder that you give me, I know the position of the hand, because these links don't change length, right? I know this is a certain length here, and I know this is a certain length here. So all I have to do is start at the shoulder, take this angle, walk out along it until I go this distance, and I get to the elbow. I then again rotate my direction using this angle, and then I walk out this length here until I get to the hand, and then I know the hand's position. That process of figuring out where something is based on an initial location and a series of parameters that describe the assembly, that is kinematics. So we would describe the process of taking a state vector, essentially, because you can imagine we now have a state vector of this thing, right? We have two angles, the theta and the phi, that describe the state of our arm, and at any time we can take, knowing the constants, in fact, let me be a little bit more explicit here. We could think of this as having sort of constants and variables, right? The constants are the L1 and the L2, right? And the variables we might say are theta and phi, but I might also include the position of the shoulder, right? Because if this can move around, then technically that's an input. Now maybe that's a constant, maybe that goes here, but it doesn't matter. Point being, the arm is completely described by these things, and which ones you want it to be constant and which ones you want it to be variable is up to you when you're describing the problem. But the point is, taking one of these state vectors, right? So, whatever we want to call this, right? Maybe we have a state vector, we'll call that S, let's say. Taking one of those state vectors and saying we've got P hand out here, I want to know what P hand is. Taking that state vector and producing the location of the hand, that's kinematics. Okay? Now let's talk about this right here, degree of freedom. Well, degree of freedom is the term that's used in this nomenclature really to talk about this state vector, right? However many scalars, right? And remember, for those of you who are math impaired, which I'm not condescending, I am not a good mathematician. A scalar is just a single floating point value, basically, right? A scalar is a single value, not a vector, just a value. However many independent scalars we have to describe our system, that is how many degrees of freedom we have. Right? And so in this case, right, it's kind of a little bit complicated. If I were to move this guy over here so that we have the constants L1, L2, and the position of the shoulder, then this is a very straightforward system. It's very easy to understand. And the reason I say that is because we have two variables here, and those two variables, as I move them, allow this arm to move around in space, right? So we have 2 degrees of freedom, and it's very clear that we do, because the number of variables and the number of actual effective ways I can move this thing is coincident, right? I have 2 axes of motion, right? I can move on the X and Y axis the hand by changing these joint angles, and I have 2 joint angles. It's clearly 2DOF throughout the system. But that's not always so clear, right? Because if, for example, I did this the other way, right? I said, no, this is a variable again. Now it's very unclear, because it would appear that we would have 4 degrees of freedom, right? I can set this angle, and this x and y, right? There's an x here and a y, right, of the shoulder. So that would look like I had 4 degrees of freedom. And in some sense, depending, like, again, there's a certain nomenclature, there's a certain formalism to the way that these things are talked about. In certain circumstances, you might say that this had 4 degrees of freedom. Okay? But in actuality, if you're talking about the result, the thing we care about, the position of the hand, there's still only 2 degrees of freedom. Because regardless of which of these things you change, you're always only changing the x or the y or both of this arm. The x and y position of the hand is the only thing you can affect. So yeah, you can change 4 different variables, but the output's only going to end up changing 2 variables, right? So the apparent 4 degrees of freedom that we look like we have when we modify our state vector end up coming down. Oops, sorry, that's our constants. End up coming out in our output as only 2 degrees of freedom. Okay. And incidentally, it's not even as simple. You might say, well, Casey, you know, the position of the hand, I know that that is a vector that's like phx, phy, or whatever. I can clearly see by looking at the output there's 2 degrees of freedom, right? So why, you know, that makes it easy. Still not easy, right? And the reason for that is, let's suppose that we constructed a different type of arm assembly. Let's suppose that the arm assembly that I gave you was an arm assembly that looked more like this. Okay? And now, what I do is I say, you don't get theta and phi anymore. The inputs to the system are theta and some function of theta, which this is set to, right? So basically, I'm only giving this, my state vector here, is only the theta. That's it. And I'm going to write an equation for this that makes it so that whatever theta I input here, I automatically slide this arm along the x-axis, right? So it never leaves the x-axis no matter what I do. Okay? If I were to do this, this link assembly would now appear to have 2 degrees of freedoms because the position of the hand does look like a vector, phx, phy. But in reality, we know that phy is constant. No matter what I set this to, it will always just slide back and forth along a fixed position in y. Right? So again, degrees of freedom can be very complicated and deceptive depending on how complex your system is. You may have to think a little bit to figure out how many degrees of freedom the system really has. Okay, so hopefully that's relatively clear. Again, we're not implementing this in Handmade here or anything like that. This is just to give you an overview of it, so you don't have to understand the specifics all that much. But hopefully that gives you a little bit of an overview of kinematics, which is taking a state vector that is describing sort of almost, you can almost think of it as a mechanical assembly. Thinking robotics tends to help. Like each, you know, there's a motor and we can set it to various positions or whatever, you know? And it, you know, it can rotate left or right, or it can rotate up or down, or both, or whatever. And so you're literally talking about what are the positions of these motors, right? And given those positions of the motors, where is the end of this thing? Okay. So I'll give you one more term here, and that is end effector. And I know since we have an effector on the chat, I feel like he'll be happy to see that his name is a formal term in robotics if he didn't know that already, which maybe he does. So typically what we call this thing, I was calling it the hand, right? I was saying the thing that we care about where it actually is when we're doing our kinematics, that is called the end effector. And it's called the end effector, I suppose, I don't really know, I don't know the history, because in robotics, where this stuff was originally sort of formalized, you cared a lot about like a grasping arm, right? You were trying to like grab things or position a robot's appendage somewhere to do some mechanical thing, like put together a car or who knows what, pick something off an assembly line. And so end effector, it was the thing at the end that you were actually trying to do stuff with, and that's what you actually cared about. So that's where inverse kinematics and kinematics sort of, started having this terminology built around them, as far as I know. Again, not a historian, so that's just my assumption. Could be wrong. All right, So that's all great, but that's kinematics. So what's inverse kinematics? Well, inverse kinematics is exactly what it sounds like. If kinematics is taking a state vector and producing an end effector position, I should say end effector, let's put it this way. Let's say if it takes a joint state and goes to an end effector state, right? That is kinematics. We input the joint state, the theta, phi, whatever. We get out an end effector state, which is the position of the hand. Inverse, why? Why does it do that? I need to disable this. Why does it have that function? That is so annoying. Stop. Okay. Anyway, inverse kinematics is exactly what it sounds like. Reverse this process. Take the end effector state as your input, right? This is the input, this is the output. And instead, tell me what the joint state is. Now, why do we care about this, right? Well, we care about this because almost all the time, when you actually are dealing with these sorts of things, this kinematics, right, is the part that the render loop does, right? Whatever the render, I shouldn't say render loop, I should just say the renderer, right? In a 3D renderer or 2D renderer or any renderer that wants to deal with articulated bodies, these, by the way, these things are often called articulated bodies. Don't ask me why, because they articulate and they're made up of rigid bodies, I guess. Anyway, this is what the renderer does. The renderer has some kind of a state, like what the joints are, and it has to produce the 3D positions of everything so it can render it. So the kinematics problem we deal with all the time, and we even dealt with this on Handmade Hero. We had the concept, right, of the hero. You know, it had a ground point, and then its head was like up somewhere offset from the ground point. That's basically a kinematic chain. It's saying, I know this, and I know that there's an offset that puts me here. Well, I need to find out where here is. That's kinematics. It's simple kinematics, but it's kinematics, right? So that's what the renderer has to do. But if you want to do modeling work, right? If I want to specify what's supposed to happen and find out what my multi-link assembly looks like, then you need inverse kinematics, because if I'm an animator or something like this, or we're on an assembly line and the robotics vision computer thing says, hey, I gotta pick up that package and I know where the package is, the location of it, it's gotta get the arm there. And the same is true for animation. The animator might say, oh, yeah, I've got this arm assembly, right? And I need it to touch this point. I need it to go reach out and grab this thing. Well, the animator doesn't want to have to fuss with these joints and like use the rotation tool to like eventually get it there. The animator just wants to say, here's where it should be. And then it wants the computer to solve for what those joint angles would be so that it touches it directly. Again, same thing with the assembly line. If this were something that the robot had to go out and like, you know, it has to weld at that point or something, it needs to solve for what it has to set its step motors to so that it knows that it's going to actually be there and actually be touching the point that it needs to touch. Okay? So inverse kinematics is very literally that thing. It's the act of taking an end effector state and producing the joint state from it such that other parts of the system, whether it's a renderer in the case of game development or an animation system, or if it's something realistic like in the real world, like a robot that actually needs to set its motors to do something, we need to know what that joint state is because it needs to feed back into the other parts of the system. Okay? So how do we do that? Right? How does that actually work? Well, it's really, really, really nasty, right? IK, as it's abbreviated, is a nasty, nasty, nasty problem. And the reason it's a nasty problem is because, well, I shouldn't say because. The reason it's a nasty problem is for two really, really tricky, nasty reasons. And really, if we're being generous, being pessimistic, we could say three reasons. Number one, inverse trig is always harder than trig. To some degree, that's the basic one. Number two, it's typically overdetermined. And if it's not, it's discontinuous. And number three, there are usually joint limits. So let's talk about these. All right, so first of all, what can I say? Even in the most simple, basic scenario that you might imagine, it's always harder to construct something that reverse solves for a bunch of trig stuff than it is to take some input angles and just produce what the thing is, right? The inverse problem is almost always harder than the original problem, and you see this pretty much everywhere, right? Matrix multiplication is a lot easier than matrix inversion, right? I mean, it's just inverting things is tricky. And so just to start off with, you can imagine, I'll just give you a very, very straightforward example. In that situation we were talking about, where I said, okay, let's pretend that we have the position of the hand, the position of the shoulder, and we just have a theta here and a phi here, okay? Knowing only what you know from Handmade Hero, you can produce the kinematics equations for this easily, okay? All you have to do is write the cosine theta sine theta vector equation, right? That rotates you theta from down. You have to go, this is the L1, this is the L2 lengths. You just multiply that vector by L1 that you get, and you would be here. Okay? That's like that. And then you know, well, okay, so if I want to know where this thing is, I just need to take this phi. It's on the inside, and I'm pointing that way, so I would just do, pi minus phi, right? To get, because this right here is 180 degrees, right? And I want to know how much to rotate this vector by that way, right? You would then take this vector, rotate it that way by pi minus phi, and then you would go L2 along it, and you'd go here. So doing forward kinematics, really not very difficult, okay? It doesn't matter how many links there are in the chain. It doesn't matter how many dimensions the problem is in. Really, it doesn't matter anything at all. It's just very straightforward to start somewhere and have a prescribed route to get to where you're going. Now, the inverse problem, we've never done anything like it on Handmade Hero, okay? If you want to try it for homework, it's actually pretty difficult. You maybe give it a shot sometime if you're interested. It's not something that will probably ever come up on Handmade Hero, but it's difficult. We've never shown how to do anything like it. It's not something I would expect you to just know how to do. Even if you're a competent 3D programmer, if you haven't ever thought about inverse kinematics before, it's a little tricky. And this is the simplest possible case. It's just a two-link. This is called two-link IK. 2D, two-link IK. Right? Because just two links. And it's kind of hard. So just for starters, it gets annoying. And the reason it gets annoying is because even in the simplest possible cases, it's harder than the forward problem. So it's a little bit nastier just right off the bat, even if we don't introduce anything else. But then we get into the bad stuff. Like, this is not so bad, right? That's not too bad. You tell me I got to solve this. It's like, okay, I can solve it. I'm not going to cry myself to sleep at night over that. But this starts to get bad. So I say typically overdetermined, and if not, it's discontinuous, right? So let's talk about this one first. So typically overdetermined, what that means is, so let's say underdetermined and overdetermined. So if something is underdetermined or overdetermined, right? And you know what I just realized? This is the wrong phrase. That's what I actually wanted to say. This is typically underdetermined, and if not, it's discontinuous. Sorry about that. Just brain flittering off into space. Okay, so underdetermined and overdetermined. What do these mean? Well, overdetermined is not such a problematic situation for us in IK because it wouldn't really be something we'd ever have to care about, so I'll tell you what it is. Overdetermined is when you have a system that has more requirements for how it has to be set up than it has variables to actually satisfy them, right? So an overdetermined system I can't really think of a way to describe what it might mean in IK because it never really comes up. I don't really know. It would be like if I said something like the hand has to be here and here, right? Like this is the position of the hand and this is the position of the hand. It's like, well, the hand can't be in two places. This is overdetermined, right? That system's overdetermined. You've given me so many requirements that I can't possibly hit them. And now you might say, well, that's just dumb. Like, why do we even have a name for that? And it's because a lot of times you actually do deal with systems like that, just not in IK. And an example, if I had to extend this bogus example into something you might actually do, you could imagine that what a graceful failure of the system would do in an overdetermined context would be to place it like in between the two of them or something, so that it's as close as possible. It minimizes the degree to which each one is unsatisfied, right? So there's a lot of other contexts where overdetermined systems make sense to talk about and you care about them. IK, not so much. I mean, maybe there is, but I've never seen that like myself, so I don't know. But underdetermined is where it's usually at. Now the reason that it's usually there is because normally with IK, you're dealing with systems that have a lot of links. So for example, one thing that I might want to do in a video game, very common, is if we go back to anatomically correct Casey, right? Obviously, this is exactly what I look like. Okay? If we were to talk about this and we were to say, I need to position Casey's hand somewhere and I want to position it over here, right? So my IK solve is trying to figure out what I would need to do to put the hand here, okay? Now, in the case where it's only a 2-link arm, all right, I'm going to go back now because this is where we need to start talking about this. You remember degrees of freedom. In a 2-link arm, the number of degrees of freedom, which were 2, happens to be the same as the output, okay? There was an X or Y output of the hand location, and there were 2 degrees of freedom that I could use to position it. So if it was a 2-link arm in a plane, okay, and I want to put it somewhere, well, that can be solved exactly, all right? It is not overdetermined or underdetermined. The number of degrees of freedom and the output space are the same. The degrees of freedom in the input space and the output space are the same. Might be a way to phrase it, right? So if we're talking about how many different variables there are in the state vector and how many variables there are on the output target, they're equal. And so, hey, great. 2 equations and 2 unknowns. This is simple mathematics. It's exact. I solve it. We're all good, right? So that works. But if I were to then say, okay, not anymore. Now I'm going to include all these joints, right? I'm going to say that Casey can stand on this leg, right? You're going to put his weight on this leg. So this stuff has to be fixed. But this joint, this joint, this joint, this joint, and this joint are all allowed to move to hit this goal. Well, even if each of these joints only had 1 angle, which really in a real situation they have more, even our 2-link, our quote-unquote 2-link one would have had more, right? Because the shoulder could be thought of as having 2 degrees of freedom because it's a ball and socket. So it can really rotate along 2 axes, right? It's got a whole sphere of movement there, right? But all of these, even if they each only had 1 degree of freedom somehow, which is a not realistic thing, they all have more than that, we would have 1, 2, 3, 4, 5, 6 degrees of freedom to play with on the input, right? But our output would still have only 2 degrees of freedom, or if this were 3D, 3 degrees of freedom, right? If this was 3D, we'd only have 3, you'd have X, Y, and Z to specify. But we'd have 6 joint angles to solve for. And that is an underdetermined state, That is a system that's underdetermined. We don't have enough equations to solve, right? So what do? Okay, no math, no amount of direct solving math is going to get you out of this scenario, because, as you know, with the algebra that you've been taught in junior high school or wherever else, grade school math, right? You know that you need one equation for every unknown. And in our system, we have degrees of freedom, which are essentially unknowns, right? We have the state vector on this side here, right? We have these variables that describe our arm. Each one of those is an unknown, and we have to solve for it. So if the degrees of freedom in the output are less than this, we will simply not have enough equations, right? Assuming that each one of these things does something, right? Has a separate thing. We won't have enough equations to generate. Now, like I said before, sometimes you can get lucky, and sometimes you can get situations where, like, remember I drew this thing, where you can say, oh, let's say there's only one input to my system, right? Let me put it to you that way. Let me put it a slightly different way. Let's say I only have one input, right? So I have like an x here, right? That I'm going to specify. And so you might say, well, there's two angles here, right? How am I going to solve for that? Well, sometimes you get lucky, and like I said, if the description of your assembly is that this is theta and this is some other function of theta that forces it to always be on the line, well, now, even though this appears like it's got 2 degrees of freedom because there's 2 joints, really those joints are dependent, so now you still only have one thing to solve for. You're just solving for theta, and so you have one input, one output, everything's good, right? You can solve that. Not a problem. Okay, so when we end up in a situation where we have a state vector that has more things we can set in it than our output has information that we can use to solve for those things, that is an underdetermined system. And that's where IK gets really nasty, because now you need some way of making up what the joint angle should be that has nothing to do with the fact that you need to end on this position. So what do? Well, one very typical thing that you might do is say, I want whatever is the thing that moves me the least from my current location, right? That's one way of doing it. Because then I say, well, okay, I know that I can try to solve for something that hits here, and I can now subject it to a minimization criteria of try to do something which moves me the least from where I am. That's now a way that I can perfectly determine my system. There is only one smallest movement or family of movements that would do that, and so now I have a shot at solving this, right? Typically I can't solve it directly still. I may have to solve it iteratively or do other kinds of fanciness, but I could do that. Another one might be solve it where there's some rest state and I want to be as close to the rest state on each of my things as possible. Another one might be try to, I don't know, I'm not thinking of a whole lot of other ones, to be completely honest with you. Try to distribute the motion evenly among all the joints. Might be another one, right? So I don't want to do everything on the last joint and hit it, or the last 2 joints. I want to spread the motion out over all the joints evenly. That'd be another way to do it. So you start to introduce these artificial criteria that are sort of based on other things, right? And then that's how you get out of the undetermined system thing. Because if you had to produce an exact solution with no other information, you would be like, I can't solve it, right? You need some other information to say, you could just give some random solution. There are ways of solving the problem so that you know that you'll hit it and it's just a random mathematical thing. But usually even those, they have something that they're actually secretly doing. Like if you look at what the math is, you're like, oh, it actually always produces the solution that does blah or whatever, right? Okay. So that's really nasty because it takes it from a problem that would just be a series of equations that you can just solve to something that's this kind of fuzzy, requires minimization, possibly iterative algorithms. Like it takes it into a whole other realm of problem solving, right? And similarly, even if you don't have that problem, for some reason, if you don't have the overdetermined thing, sorry, underdetermined thing, you have typically another problem, which is that oftentimes it's discontinuous. And what that means is if you were to write equations that do solve it directly, so they are actually, like, you have a situation where you have the 2 link ik, right? And you wrote the equations for solving for the end effector in terms of these 2 angles directly. Typically, those direct solutions end up being discontinuous. So, like, when you move this thing smoothly, so I move it like here, 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 and here, right? It moves it like, it does like this, and then it like pops to that, right? Because usually there's some positive negative term in here, because you can almost see it if you just think about the problem, right? If I told you to put the thing here, right? Here's the position of the hand, here's the position of the shoulder, right? Well, for any solution that I give, right? Yes, there's only one solution in this quadrant that can satisfy this, but I could always take the negative flipped version, and that also solves it. So even though it's basically a solution, usually, and this is because of the trigonometric nature of it, right? There's a positive negative possibility in there. All the solutions can have a positive negative choice in them. And so typically you end up in situations where even there'll be like a singularity in here where there's no way to really make it move smoothly through that point without having it flip, and you just have all these other nastinesses. Again, not something you need to really think too hard about. I'm just kind of pointing them out as things that happen in IK. And finally, if all of that weren't nasty enough, we've got nasty number 3. And nasty number 3 is that usually nobody wants you to actually solve this problem in such a clean fashion as what I just suggested. Normally, it's not, oh, hey, here's just some joints, and here's the theta, and theta can be whatever you want. It's like, no. Theta cannot be whatever you want, typically. Really, what normally happens is something more like this. We built this robot, right? And it's got, a range of motion that's like this or something. So the joint that comes out of here cannot go past this point. This is like a hard limit. And it cannot go past this point. And that's true of the human body too, right? You can't rotate your arm any further than this, right? I can't rotate it through here. Okay, that's just the way physical things work. They hit stuff. So, if you're animating a human, you've got all these joint constraints. Similarly here, right? This elbow, it can't bend past here, right? It's got to be up, and it can come all the way back here, but then it can't bend past there. Okay? So now, not only do you have this problem of I keep saying overdetermined, underdetermined systems, and a nasty inverse problem you got to solve, but now you also have to deal with boundary conditions that are basically saying like, oh, okay, there's constraints on this problem where the answer is constrained to lie within this value and this value, so you can't just solve it for anything. You have to solve it in the space that's in there. And so that interacts with this determination problem where you kind of have to do these systems that go like, oh, okay, try some things and iteratively try to figure out, can I move it here? Do I need to move this joint over there? Blah, blah, blah. Could be really nasty because math traditionally is pretty bad at dealing with these sorts of things. They turn into these things, they're called, well, actually, I think the entire domain is called operations research. Right, and what's the general name for the problem if you actually solve these directly? It's called, I can't believe this is not something I remember. This is going to drive me nuts. So in operations research, there's a name for this kind of a problem where you're doing solves that it's a nonlinear, it has constraints, and it's got a minimization criteria. And it's called, oh man, this is why getting old is awful. Do not ever, basically stay 27 or so for as long as you possibly can. Do not ever hit 30. Try to have an asymptotic age so that every year you get older by half as much as you got older the previous year, so that you just never, you can live the rest of your life and never get past 29. It's not, so there's a special case of it called Danzig's algorithm. That's not the one that I mean. This is a special one that has constraints, that has additional qualifications to it. It's called... a linear complementarity problem. So I believe a linear complementarity solver is the one that does all these things. And they're very complicated. Let me see if I remember that. Yes, I think this is it. Yeah, so I'm pretty sure Lemke's algorithm is the one I was thinking of. And it is a linear complementarity. Okay. I may have just fished that one out. We'll have to wait for the chat to referee it to know if it's actually correct. But I'm pretty sure that that's called a linear complementarity problem. And so you need a linear complementarity problem solver if you're going to solve it. Lemke's algorithm sounds really familiar to me, so I think this is that I'm correct in the name here. So that is really big, bad, ugly math. It's pretty tricky. They're like basically these iterative solvers. Some of them are direct solvers, but they still operate iteratively, essentially. And others are like solvers that are converging solvers that you run over time, and their answer gets refined. And yeah, you know, if you, basically anything that we do on Handmade Hero that in terms of math solving is nothing close to how bad these guys are. They're just nasty. And thankfully, like lately, I think, if I remember correctly, they've gotten kind of better at doing iterative versions of them that aren't so complex and aren't so numerically unstable as they used to be. So it's probably better now than it was. But point being, not what you want for a cakewalk. Like you don't want to hear someone say, if you can avoid it, that we need a linear complementarity solver for this thing. So really nasty. And a lot of times in IK, they just cheese it. They don't actually use anything like this. They'll actually just use some kind of cheesy, half-baked, iterative thing that just kind of moves joints generally towards the goal. And that tends to be good enough. So sometimes you can do sort of cheesy stuff. There are some pretty simple algorithms that work okay. And that is actually what people often use instead of like trying to do things that are extremely mathematically rigorous for them. So yeah. So nasty, nasty, nasty problem. It's just a really bad problem. As I alluded to there, though, if you need to use it, the good news is that usually, most of the time, and not all the time, so, I apologize for those of you who are not in this circumstance, but most of the time, you don't really need to mathematically accurately solve IK problems in that sense, right? Because if you think about it in like an animation context or something like this, it's not really about getting a precise mathematical answer, right? And so you're just looking for something that achieves the goal of positioning a leg, or a foot or a hand at a location reasonably well. And so even though this problem specification is super nasty, as I sort of said just moments ago, there are some cheesy algorithms that work reasonably well, so you can use it in a game context and not be too worried, especially if you're just using it for fix-up, right? So for example, if you're just trying to take an animation that somebody made and adjust the position of the hand so that it hits something exactly that's like on the ground or whatever, like it's a pickup animation, and I want to adjust it so that it hits whatever it's picking up exactly, that's not so hard. A simple iterative thing that moves the joints a little bit, and there's been a number of papers on this sort of thing, will work. So yeah, I just wanted to get across how nasty the problem was, but I don't want you to like go cry in despair or anything. If it is something you need to do, there are lots of approximate sort of things that look fine when you do them that maybe aren't really rising to the level of qualifying as solving the problem in the mathematical sense, but that's not really what you needed. You usually only need a solve in the visual sense, and there are plenty of options there. So that's the good news, if that makes any sense. So that's about it. Hopefully, that gave you some background on the inverse kinematic situation. Yeah, we're pretty much out of time, so if you have questions on it, we can always take them tomorrow. But that's pretty much what there is to it. You know, if we were to go any further into it, we'd have to start talking about actually how you solve it, right? Like, you'd actually start coding a solver or something from here and talking about the different stuff. But, so yeah. All right. So I'm going to go ahead and wrap up. Oh, wait, I see a question here. Mr. Fourth Dimension, I would think boundary conditions would help to move towards being more determined, so why don't each of those two problems reduce the severity of the other? So the reason is because math is really bad at inequalities, right? So if I tell you to solve the equation 2x plus y equals 4 and x plus 3y equals 6, this is what math excels at really, really well, right? If instead I tell you to solve the problem 2x plus y equals 4 and, you know, x plus 3y is less than 6, well, this doesn't really help all that much, right? Kind of what this did is just make things more complicated for you, because now you have to sort of talk about a family of solutions, a half space, right? And carving spaces in half doesn't really help you. It actually makes things more difficult because now, instead of having a free variable, you have a free variable up to a point, right? So it's really just the difference between this, which is always helpful, and this, which is really just further complicating. And it's not to say that it doesn't limit the space of solutions. It obviously does. But it doesn't limit them in a way that math takes advantage of very easily. And sometimes it's actually a way that makes math harder, because now you can't just solve for variables or reduce to a single variable that varies, because now there's actually like a hard cut in the space of solutions that nothing can be on one side of, but everything could be on the other side of. Hopefully that makes some sense. Elvin, thanks for the awesome answer. I was intending to use IK to solve for foot placement on uneven terrain, so we have an animation of the dude moving and want to place his foot correctly on the ground. Is that hard? No, it's not too hard. I don't know what the latest state of the art in IK in easy IK is, but you know, there's like recursive descent versions that are super trivial to implement. And I think they're called possibly iterative descent, maybe. But like the super trivial ones to implement that actually work fairly well for stuff like that is, you know, I've got the leg. Well, let me do the side view. So the problem, right, is the animation placed the guy's leg here, and that's just obviously totally wrong because it's underneath the ground, right? This is the ground. This is the foot. So I want the foot to be up here. So what the iterative descent ones do, they're really, really straightforward. What they do is they say, well, okay, if I needed to move this guy to here, right? I'm trying to remember exactly what this does. I think what it does is it says, like, the vector from me to the end effector, right, whatever that is, try to rotate that so it faces why can I not remember this? So basically you run this multiple times. I think it's that you take the vector from the location of the joint you're going to work on. So you start at like the root, let's say, and you say, all right, I've got a vector from here to here. Okay, I rotate it so that it's in line with this thing. Right? So basically it points like that. Then I take the next joint, right? and I've got that line from here to here, and I rotate it so that it points along, so that it's coincident with this thing. Then I just start again. So I come back up here. Now my end effector direction is here, right? So now I rotate it again. So I got to rotate it this way, right? So that my line is here. And then it just, I'm not drawing this very well. Let's draw it one more time. Okay. So I want to move this foot up. Target is here, right? So I first take this vector, and I say I want this vector to point. All right. So this is the vector from the end effector. I'm sorry, from the joint we're on to the end effector. I want to rotate so that this points directly through there, right? So that moves me up a little bit here, right? Then I've got this guy, it's out here, and I look at that and I say, well, I want to rotate that in, right? Because I want, again, I move to this joint and I do this joint so it points in that direction. I then start again here, and I would see the same thing. I see it down there. I got to move it up so it rotates up a little bit, and then again it's out so it moves it in a little bit, right? And eventually it will hit. So you just do, you do like 10 iterations of that thing, or you can iterate up to like 1,000 times or something, but stop when you get close enough to your goal. You can choose how you want to budget your time or however you want to do that, right? But within, 10 iterations or something like this, it's going to be pretty darn close to the goal, and then you could stop. And that's really easy to implement joint constraints in, because then when you do your rotation, you just never let yourself rotate past the joint constraint. This is pretty good for IK fix-ups. It's not so good for whole body solutions, whole cloth, because it'll hit joint constraints and not realize it should kind of rotate out of them, so it gets caught in local minima, right? Or local maxima, I should say. So yeah. Let me see. Cyclic coordinate descent. That's what it's called. I forgot the name of it. Cyclic coordinate descent is the thing. So cyclic coordinate descent is like totally fine for this sort of thing. I would suspect, because I haven't done character animation work since 2003 or 4, right? I would suspect that by now there's a better simple technique. Even cyclic coordinate descent was not the best technique for IK even in its time, but it's the easiest. It's very, very easy and produces reasonable results. There might be ones that's similarly as easy now that people have figured out that produce good results. So you might want to do a survey of the literature really quickly, because, you might get lucky. I don't know. But anyway, there you go. All right, I'm going to close it down because we are out of time. And yeah, that's really all I have to say about that. That's really all I have to say about that. So, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like more chats until we're off RSI break, I will be back here tomorrow, 5:30 Pacific Standard Time. I'd love to see you. I hope you'll be able to make it. Until then, my friends, have fun coding, and I will see you on the internet. Take it easy, everyone.